Let's consider the definition of exponents. In particular, let's start with positive integer exponents. Informally, positive integer exponents denote repeated multiplication. For any real number a to the nth power means a product of n factors of a. For example, 2 cubed equals 3 factors of 2 multiplied together, producing a product of 8. 3 to the 4th power equals the product of 4 factors of 3 multiplied together, which yields 81. The fraction 2/3 raised to the 4th power means 4 factors of 2/3. By fraction multiplication, we multiply the numerators, multiply the denominators, and we get 16 over 81. When dealing with exponents, we need to consider some notational conventions to avoid ambiguity. In particular, if an exponent applies to a base with more than one symbol, parentheses are required. For example, -3 squared equals -3 times -3, which is 9. But -3 squared is -3 times 3, which is -9. The exponent here doesn't apply to the negative sign because the exponent only touches the 3. Similarly, in 2 plus 3 squared, the exponent only applies to the 3. So we get 2 plus 9, which equals 11. If we want the exponent to apply to the sum of 2 and 3, we need parentheses to indicate this, as in the final example given here. For a formal mathematical definition, we give what's called a recursive definition. A recursive definition indicates how to get from one value to the next value by iterating a constant process. For any real number a and for any positive integer n, we start by defining a to the 1 equal a, and a squared equal a to the 1 times a. Then to get the n plus first power of a, we multiply the previous a to the n power by another a. For example, the 5th power of a equals the 4th power of a multiplied by another factor of a. Similarly, the 6th power of b is the 5th power of b multiplied by another factor of b. This formal recursive definition of exponents comes in handily in advanced math classes.